Okay, if you're watching this video, this is a review from the homework that was due on Wednesday, December 16th by midnight. It eventually ends with having to write balanced equations, net ionic equations, or complete ionic equations, then net ionic equations. So this worksheet kind of starts you off easy. The first set of four says to identify which type of reaction it is and balance each equation if necessary. So this equation is a synthesis reaction, because you have multiple reactants, you have one product. But I see that we have two nitrogens on the left, one nitrogen on the right, two hydrogens on the left, three hydrogens on the right. So work with the 2 to 3 difference. They have a common multiple of 6, so you want to get both of them up to 6. So put a 2 coefficient in there, a 3 coefficient in there. So you would rewrite the equation: nitrogen reacts with 3 moles of hydrogen to yield 2 moles of ammonia gas. So this is a 1 to 3 to 2 ratio. For the next equation, this is a decomposition reaction, because you have one reactant and multiple products. Now I also want to go over with you guys why these are in the ratios that they are. This compound right here is called calcium hydroxide, or excuse me, calcium carbonate. Calcium has a positive 2 charge. Carbonate has a negative 2 charge. So they balance out each other 1 to 1. Calcium has a positive 2 charge, and oxygen has a negative 2 charge, so they balance out each other 1 to 1. And then carbon dioxide is a molecule. And so I know that because there's 2 nonmetals, carbon and oxygen. So that's why we call it carbon dioxide instead of just carbon oxide. So this looks like it is already balanced. It is a 1 to 1 to 1 ratio. The next we have selenium reacts with oxygen to form selenium trioxide. So this is going to be a synthesis reaction. I know that you see oxygen as a reactant, but there's multiple reactants, one product. So it is not balanced. So let's rewrite it so that we can balance it. Looks like we're going to need 2 seleniums. We're going to have 3 moles of oxygen gas, and that is going to yield 2 moles of selenium trioxide, and that is balanced. And then this last equation is a combustion reaction, because you see oxygen is a reactant and carbon dioxide and water are products. Okay, so it looks like we have ethene reacts with oxygen to yield carbon dioxide and water. It is not balanced, so let's rewrite it so that we can balance it. So put a blank for C2H4, reacts with a blank for oxygen gas to yield a blank for CO2, and a blank for H2O. Okay. Looks like we have 2 carbons on the left, 1 carbon on the right, so let's put a 2 right there. And if it's wrong, you can erase it and start over. You have 4 hydrogens on the left, you have 2 on the right, so put a 2 right there. Looks like we have a total of 6 oxygens on the product side, you put a 3 right there, and we are balanced. So this would be a 1 to 3 to 2 to 2 ratio. Okay. Let's move on to single replacement reactions. So in a single replacement, this is where the more reactive something is, the more it can replace it. Now this list has a typo in it. It has iron above and below. Iron is above copper. I don't know why they have that there, but let's get rid of it. Okay, so we have chlorine gas and potassium, aqueous potassium iodide. We need to see if we can finish the reaction. Now this list that they provide you only has the metals, but if you wanted to do the halogens, the activity series looks just like it does on the periodic table. Fluorine on top, then chlorine, then bromine, then iodine. Any element below another cannot replace the one above it. So we have chlorine gas It's diatomic. Reacts with aqueous potassium iodide. Potassium and iodide have a positive, or excuse me, potassium is a positive one charge and iodide is a negative one charge. Okay, so we continue and we have to figure out, can chlorine replace iodine? The answer is yes, because if you look at the list, chlorine is above iodine, and so it can replace it. And so we're going to have KCl, that's going to be aqueous, reacts with iodine, which is a solid halogen, so I know that's in the solid state. Now, this is not balanced, so let's balance it real quick. We're going to have a 2 right there and a 2 right there. So the ratio is going to be 1 to 2 to 2 to 1. There is your balanced complete single replacement reaction. Next, we have magnesium metal. So it's going to be magnesium, and it's solid. Reacts with aqueous copper 2 sulfate. Now, as I was said in class today, I want to be sure you guys know how to balance individual compounds appropriately. This is copper 2, it says so right there. This means it has a positive 2 charge. Sulfate has a negative 2 charge, so they balance out at a 1-to-1 ratio. That's why I have it in that arrangement. So we need to look and see, does magnesium have the ability to replace copper? Well, there's magnesium, there's copper. Magnesium is above copper, so the answer is yes, it can. So let's go ahead and finish it off. Magnesium is going to replace copper. So I have magnesium sulfate. That will be aqueous. And then we'll have copper over here by itself. Now notice that magnesium sulfate is in a 1-to-1 ratio because magnesium is positive 2, sulfate is negative 2. Okay? And let's check to see if it is balanced. It is balanced. It's going to be a 1-to-1-to-1-to-1-to-1 ratio. All right, next we have copper metal and iron 3 chloride. In water solution. Now the reason I made this 1 to 3 is this said iron 3, so that's a positive 3 charge. Chloride is a negative 1 charge, so you need 3 chlorides to balance out the 1 iron. Can copper replace iron? Well, here's copper, but iron is above it. So the answer is no, it can't. So you just put NR, no reaction. Don't even worry about balancing it. All right, let's do the last one. We have lead metal. Lead is Pb. It will react with aqueous silver nitrates. Silver is Ag. Nitrate is NO3. Now, how do I know it's in a 1-to-1 ratio? Well, silver is always positive 1, and nitrate is negative 1, so that's going to be a 1-to-1 ratio. Does lead have the ability to replace silver? Well, it's not even on this list, but I can tell you that silver is near the bottom of the list. And so the answer is yes, it can. Now, here's a dilemma that I can understand you guys would have. Lead can either be positive 2 or it can be positive 4. How are you supposed to know? You really weren't. So if you had trouble with this one, I can understand that. So let's just pretend that this was lead 2, okay? So we will have lead 2 nitrate. The lead is a positive 2 charge, the nitrate is negative 1, that's why I made 2 nitrates, and then silver is going to be over here all by itself. And then you have to balance it, so we need 2 in front of silver nitrate, and a 2 in front of silver, and we're good. All right. Let's get to the double replacement reactions. Write a balanced chemical equation for each of the following double replacement reactions. Here we go. A water solution of zinc bromide and a water solution of potassium hydroxide. Did my little, that's my problem. I never write it down. Form a water solution of potassium bromide and a precipitate of zinc hydroxide. Okay, I want to go over all these so you guys know, why did I put Z in Br2, KOH, KBr, ZnOH2? Zinc is positive 2 charge, always. Bromine is negative 1. You need 2 bromines to balance out the zinc. Potassium is positive 1. Hydroxide is negative 1. That it balances out 1 to 1. Potassium is positive 1. Bromide is negative 1. That balances out 1 to 1. And zinc is positive 2. Hydroxide is negative 1. You need 2 hydroxides to balance out the zinc. So that's the justification as to why I chose those ratios. Okay. Let's balance it out. Just by looking at it, it is not balanced. We have 2 bromides on the left, 1 on the right. So let's put the 2 coefficient in front of potassium bromide and a 2 coefficient in front of potassium hydroxide. And it looks like it is balanced. So this is going to be 1 to 2 to 1 to 2 ratio. Next, a water solution of copper 2 sulfate and a water solution of barium chloride produce a water solution of copper 2 chloride and solid barium sulfate. Okay, let's go over why I chose the ratios. We called it copper 2, so it's positive 2 charge. Sulfate has a negative 2 charge, so they balance out 1 to 1. Barium has a positive 2 charge. Chloride has a negative 1 charge, so you need 2 chlorides to balance out the barium. Copper has a positive 2 charge in this case. Chloride has a negative 1 charge. You need 2 chlorides to balance out the copper. And barium is positive 2, and sulfate is negative 2. Okay? All right. So that's the unbalanced equation, but maybe it is balanced. Let's check and see. 1 copper, 1 copper, 1 sulfate, 1 sulfate, 1 barium, 1 barium, 2 chloride. Yeah, it's balanced. So it's a 1 to 1 to 1 to 1 ratio. Okay, now, finally, careful on how you read this one because it reads the products first. And then it says the reactant second. It says a precipitate of iron 3 carbonate in a water solution of sodium nitrate are formed when a water solution of iron 3 nitrate in aqueous, almost forgot, in a water solution of sodium carbonate we have a precipitate of iron 3 carbonate and a water solution of sodium nitrate. Okay, so I want to go over why I chose these ratios. We call this iron 3, so that is a positive 3 charge. Nitrate has a negative 1 charge. You need 3 nitrates to balance out the iron. Sodium has a positive 1 charge. Carbonate has a negative 2 charge. You need 2 sodiums to balance out the carbonate. These irons have a positive 3 charge. The carbonates have a negative 2. So you need 2 irons and 3 carbonates to be able to balance them out because positive 3 times 2 is positive 6, and negative 2 times 3 is negative 6. And then sodium is positive 1, and nitrate is negative 1. That's why the ratios are what they are. Now, let's see if it is balanced. Let's see. We have 2 irons over here. I'm actually going to do a scoreboard for you guys because this one is a little confusing. Okay, looks like we have 1 iron, 1, 2, 3 nitrates, 1, 2, 3, 4, 5, 6, 7, 8, 9 oxygens, 10, 11, 12. We have 12 oxygens. We have 2 sodiums and 1 carbon. Let's look over here. We have 2 irons. Looks like we have 1 carbon, 1 sodium, 1 nitrogen, and 6 oxygens. Okay, so it's definitely not balanced. Let's balance it out. I would put a 2 in front of here to get the irons balanced out. So the irons are good, but that's going to distribute across all of this. So we have 3 times 2, we now have 6 nitrogens. Let's see what else we need to do. There's 2 sodiums here. Let's put a 2 right there. We now have 2 sodiums. We have 2 nitrogens. And we have 6 oxygens. 6, 7, 8, 9. It's actually looking like you're going to need to put a 3 here, and we're going to erase this 2 and put a 6 in front of it. So let me just make a few adjustments here. Okay. Put a 6 there. So we now have 6 sodiums. We now have 6 nitrogens. We have 6 sodiums over on the left. And for oxygens, okay, here we go. Let's count them up. 6 times 3 is 18. 19, 20, 21 so far. But I believe we're going to have to go higher than that. We have, yeah. Oh, wrong ones. Okay, let's look at the oxygens over here. 3 times 3 is 9. 3 times 3 is 9 times 2 is 18. 18 plus 9 is 27. So we need to get this oxygen number up to 27. Let's see, how are we going to do that? Okay, made a little mistake here. So we need 3 of those. There we go. That was my mistake. Okay, so that's going to equal 27 total oxygens. 5, 10, 15, 20, 25, 26, 27. There you go. It's a balanced equation. So the ratio is going to be 2 to 3 to 1 to 6. My mistake here was, here's what I wrote. That was a mistake. I should have wrote this. That makes it a 2 to 3 ratio. So I left that 3 out. All right. Now, let's go to the next part. We need to write the complete ionic, and the net ionic equation. So here's what I'm going to do. I will do the chemical equation in red. I'll do the complete ionic equation in blue. And I'll do the net ionic equations in green. All right? Here we go. Aqueous solutions of potassium iodide and silver nitrates are mixed, forming a precipitate silver iodide. Now you can't, I know that it did not mention the other reactants, but just because it didn't mention nitrate and potassium doesn't mean you ignore them. So you still have to write them out and finish it off. And that is potassium nitrate. They're all at a 1-to-1 ratio. +1, -1, +1, -1. Oops. +1, -1, +1, -1. So they're all a 1-to-1 ratio. the equation is balanced. Oops, I'll fix that, put that 3 back in a second. Okay, for the complete ionic equation, here we go. Potassium ion plus an iodide ion plus a silver ion plus a nitrate ion reacts to produce silver nitrate solid and a potassium ion and a nitrate ion. All right, so now let's do the net ionic equation. You eliminate whatever you see on both sides. So I see potassium there and there, they're gone. I see nitrates here and there, those are gone. So you just write what's left. So we have an iodide ion reacts with a silver ion to produce solid silver iodide. Okay, let's keep going. Aqueous solutions of aluminum chloride and sodium hydroxide are mixed, forming the precipitate aluminum hydroxide. And the rest of it would be sodium chloride. And it is not balanced. But before I get to balancing, I want to show you why I chose these ratios. Aluminum is +3, chloride is -1. Sodium is +1, hydroxide is -1. Aluminum is +3, hydroxide is -1. Sodium is +1, chloride is -1. So you need a 3-to-1 ratio for aluminum chloride and a 3-to-1 ratio for aluminum hydroxide. Okay, let's balance this. Looks like we need to have a 3 there and a 3 here. I think that's good. So it's a 1:3 to 1:3 ratio. Next, the complete ionic equation. Aluminum ion plus 3 chloride ions plus 3 sodium ions plus 3 hydroxide ions yield aluminum hydroxide as a solid, 3 sodium ions, 3 sodium ions and 3 chloride ions. Okay, and then you eliminate whatever you don't, or what you do see on both sides. So I see 3 sodiums, 3 chlorides, 3 chlorides. Everything else stays. So we have an aluminum ion that is aqueous, reacts with a hydroxide ion, which is aqueous, to yield aluminum hydroxide, which is a solid. All right, a few more. Let's see, we got 1, 2, 3, 4 more. Same thing, I will use red, blue, and green. Mixing sulfuric acid, H2SO4, and aqueous potassium hydroxide to form aqueous potassium sulfate. Now, you might be wondering what happened to the water, or what happened to the rest of it. So You got potassium and potassium. Okay, that's there. You got sulfate and sulfate. That's there. What about everything else? It produces water. It says right there. Don't forget that. Water. Water is going to be liquid. All right, so we have 2 ions of hydrogen reacts with 1 ion of sulfur. I didn't balance it though, did I? That's my fault. So let's go back and balance this. Should be 2 there. 2 here. I think that's good. Yeah, that's good. So it's a 1 to 2 to 1 to 2 ratio. All right, let's do the complete ionic equation. You need to ionize everything that is aqueous. So we have 2 ions of hydrogen, 1 ion of sulfate, 2 ions of potassium, 2 ions of hydroxide. You have solid potassium sulfate, and you have liquid water. Okay, well, with this problem, you don't see anything repeating on the other side. So this is also, not only is this a complete ionic equation, it is also the net ionic equation too. There's really nothing to break apart. Oh, wait, no, I'm wrong. It says aqueous potassium sulfate. So I was wrong. Let's fix that. So we do need ionizing. Here we go. So that stays, and that stays. This should have been 2 potassiums and 1 sulfate. Okay, so 2 potassiums, 1 sulfate, 1 sulfate. All right, so we have 2 hydrogens react with 2 hydroxides to form 2 H2Os. There's your net ionic equation. All right, next, mixing nitric acid, HNO3, and aqueous ammonium hydroxide produces water. And ammonium nitrate. Okay. Hydrogen is a positive 1 charge, nitrate is a negative 1 charge. Ammonium is positive 1, hydroxide is negative 1. Ammonium is positive 1, nitrate is negative 1. That's why those are in the ratios that they are. It's all 1 to 1, so it should be balanced. Okay, let's do the complete ionic equation. One hydrogen ion, 1 hydroxide ion, 1 ammonium ion, 1 hydroxide ion, liquid water, 1 ammonium ion, 1 nitrate ion. Okay, and then let's eliminate what you do see on both sides. So I see ammonium and ammonium, those are canceled out, and I see nitrate and nitrate, those are canceled out. So your net ionic equation is going to be very similar to the previous problem. There's your net ionic equation. Okay, 2 left. Perchloric acid, HClO4, reacts with aqueous potassium carbonate to form CO2, which is a gas, water, which is liquid, and then whatever's left. So some of you said this gave you some problems. Well, you have potassium, you have chloride in there. So those are going to break apart. So you have potassium chlorate. This has a positive one charge. So this means that chlorine must have a negative one charge because there's only one of them. So you're going to have KClO4. That will be aqueous. All right, let's see if it is balanced. I don't think it is. So we have 2 potassiums on the left. Let's put 2 on the right. 2 there. And I think it's balanced now. Let's check. 2 hydrogens on the left, 2 hydrogens on the right. 2 chlorates on the left, 2 chlorates on the right. 2 potassiums on the left, 2 potassiums on the right. 1 carbon on the left, 1 carbon on the right. And 1, 2, 3 oxygens. Yep, it's balanced. Okay, let's go and do the complete ionic equation. Oop, wrong color. We have 2 hydrogen ions, 2 perchlorate ions, 2 potassium ions, 1 carbonate ion. We have carbon dioxide gas. You don't break that apart. We have liquid water. You don't break that apart. We have 2 potassium ions. And we have 2 perchlorate ions. Okay. You then eliminate what you do see on both sides. So I see 2 perchlorates, those go. I see 2 potassiums, those go. Everything else stays. So we have 2 hydrogen ions. We have 1 carbonate ion. And that will yield carbon dioxide gas and liquid water. Okay, 1 more to go. Hydrobromic acid, HBr, reacts with aqueous ammonium carbonate forms carbon dioxide, water, and then you have to come up with the third product. Looks like we have something with bromine, and we have ammonia, so we need to put ammonium bromide. Now, before I go to balancing, I want to be sure you guys understand why I chose the ratios I chose. Hydrogen is +1, bromine is -1. Ammonium is +1, carbonate is -2, so you need 2 ammoniums. And then ammonium is +1, bromide is -1. Okay? Let's go to do the complete ionic equation. Oh, wait, actually first, let's balance it. I think we need 2 ammonium bromides there, which means we need 2 hydrobromic acids there. And I think it's good to go. Yep. All right. Here we go. Two hydrogen ions react with 2 bromide ions, react with 2 ammonium ions, react with 1 carbonate ion to form carbon dioxide gas, to form liquid water, form 2 ammonium ions, and 2 bromide ions. Yeah, that was a big one. All right, eliminate what you see on both sides. There are 2 ammoniums and 2 bromides on the other side, so let's get those out of here. And keep everything else. Here we go. 2 hydrogen ions react with 1 carbonate ion to yield carbon dioxide gas and liquid water. All right, that is it.